Okay, we were discussing about the recurrence relations in algorithms, and we discussed the case when the functions we were having were the decreasing in nature. That's a recursive call was made, and that recursive call, inside the recursive call, we were decreasing the parameter each instance of time so that the recursive function will ultimately terminate to some goal. And this we saw using the two methods for solution of the recursive relations. One was the recursive tree method, and another was the substitution method. So what we saw till now is that when we had a recurrence relation of the type like t of n minus 1 plus 1, this was one type of recurrence relation we were dealing with. The second type was t of n minus 1 plus, here it was n. This was the second type of recurrence which we solved in the class. T of n minus 1 plus log n. And this was the third type of the recurrence relations. All of them are the decreasing functions, and we have used two methods to solve them. And what we saw is that while solving those different recurrences, in this case, we got its final complexity as order of n. And for this one, that's t of n minus 1 plus n, it was of order of n square. Similarly, for this one, we got order of n into log of n. And I said that whenever you see any recurrence of this form, any recurrence means t inside there is something which we are decreasing to the n, even if it is 99. Anything which we are decreasing to n minus something, plus there is some function, we will denote it like this plus, we will denote it is a kind of function. Sometimes it could be 1, sometimes it could be in the power of n, and sometimes it could be in terms of log n. So at that very time, whatever is your function, that is whatever is on the right hand side, that's fn, its solution will be such type of recurrences will be having the shorthand solution as n into f of n. Simple. That's whatever is f of n, multiply that with n. Because if you take any example out of them, here f of n is 1, so we will multiply it by 1, that will become our its order. Here f of n is n, we will multiply it by n, it will become order of n square. Here f of n is log n, when we multiply it by n, it becomes n into log of n. But this is the case when we saw our recurrence is of this form. But we also solved recurrence which is like 2t n minus 1 plus 1. This type of recurrence we also solved. So in those cases, there was no coefficient or no multiplier term to the t. It was 1 at every stage. But there could be some examples where there is this multiplier or there is this coefficient by which we are multiplying this recurrence. And at that very time, we got its solution as 2 power n. 2 power n. And now if it will be like 2t n minus 1 plus here it will be n in place of that. So again, what we had to do is 2 power n into f of n. F of n is this thing, whatever is on the right hand side. So in this case, we also multiplied it by the f of n, but that was equal to 1. Okay. So whatever is this coefficient, take it, its power equal to n and multiply it by f of n. That is what is on the right hand side of this recurrence. So if we make a general form, a general representation of whole of those recurrence relations, we can say that a recurrence is of the form, it's like t n minus, in place of something which we are decreasing to this n. we will denote it by a variable by the name of b. Okay, because each time we are decreasing the function value, the parameter, by some value. So if we don't write it as 1, 2, 3, 99, whatever, we write it as a variable so as to make a general equation for this recurrence. So we write it t of n minus b. At each time there is some multiplication factor to t on the left hand side. In those cases it is equal to 1, 1, 1, but sometimes it is equal to 2, sometimes it could be equal to 3, anything. So we will denote it by a variable by the name of a. And similarly, we will add. Now there is one more term in this recurrence, that is something is added to this whole, and that we will denote by f of n. Sure. This f of n is sometimes 1, sometimes it is n, sometimes it is log n. Okay. And this a and b terms are what is present inside these recurrences. And such type of, when we represent all the recurrences which we solved till now, whether these were of this form or these were of this form, when we represent all such recurrences in a general form, if you substitute any value of a, any value of b, any value of f or m, you will get all these recurrences which exist in the case of decreasing functions. And such type of representation is known as master theorem. But master theorem for what? Decreasing functions, because we did not deal with dividing functions till now. Master's theorem for decreasing functions. So Master's theorem is a general way of representing whole the recurrences relation using a formula in which when we substitute the values of different parameters, we get multiple number of the recurrences of decreasing nature. And Sam, if you see here, this is the general representation. I have also taken t of n equal to a t n minus b plus f of n. And hold those equations which we solved on the left hand side, these can be represented as by this one equation. Now, to solve this general form of equation, this Master's theorem for decreasing functions, there can now exist three different cases. And what we are assuming in this Master's theorem is that a should be greater than 1. Similarly, b should be greater than 1. And similarly, this f of n is n to the power of k, if you see it clearly. Because, you know, when we took these recurrences as example, here f of n was equal to 1. That will be also written as n power 0. So n power k means k is equal to 0 at that very time. Okay. Now in the second case, f of n is equal to n, this. So it will be represented n power 1, which again means k is equal to 1. So similarly, any function or any this f of n could be represented in powers of this n power k. And we assume that k should be greater than or equal to 0, because it can be equal to 0 or could be greater than also, but not in negative terms. Okay. Now, to solve this Master's theorem, which is the general theorem, we can have three different cases. We can have three different cases. Okay. So if we see the case number 1 is that when a is equal to 1, when a is equal to 1. So when a is equal to 1, here in this, if we write it down for the case first, it will be t of n minus b plus f of n. Okay, this will be what it will be equal to, because in place of a, we are substituting it equal to 1. And if you match this recurrence with all those recurrences whose example we have taken here, this is equivalent to those t of n minus something plus f of n. And what we saw at in such situations, when our recurrence is of this form, its solution is equal to n into f of n. Yes, that could be also written as n into n to the power k. Yes. So now if you substitute any of the values here in this general form for case 1, you will get all those recurrences which we solved. So if we substitute, already a is equal to 1. Now if we substitute b is equal to, for example, 99, and f of n is equal to n, what we will get is equal to t of n minus 99 plus f of n minus n. So we got all those recurrences which come under the case 1, and without solving it using any of the methods, recurrence tree, substitution, you know now that this is a special case of Master's theorem, and it comes under the case 1. And the case 1 solution is simply what you do, you take this equal to f of n and multiply it with n. So this will become equal order of n square. And this will be valid for every recurrence, whatever you take. So that is why this master method is the way of generalizing the things in this case. So now a is equal to 1. A could be greater than 1 also, because we took some examples of a where a is not equal to 1, it is greater than 1. It could be 2, 3, anything could be here. So this type of recurrences come under the case second. When something is multiplied as a coefficient to t, then this recurrence comes under the case 2. And we know in such cases our solution is what? Our solution is that the coefficient term here it is 2. So the coefficient term has to be raised to the power of 2 power n, and it has to be multiplied by f of n. Because here it is 2 to the power n, f of n is equal to 1. That is why it came out to be 2n. In this case, it could be 3 to the power n, and in place of f of n, we are having n, which means n 3 power n. So for case number 2, as it is given here, if a is greater than 1, so whatever a is, means whatever the multiplying factor is, multiplying term is, take its power as a power n, 2 power n, 3 power n, anything, and multiply it by f of n. And you will get all those recurrences of this form. This becomes the case 2. So here is that whatever is coefficient, whatever the coefficient is, take its nth power and multiply it by f of n. That will give you the solution of the recurrences which come in the case second when a is greater than 1. Now the third case may be that, so without looking to the values of b f of n, the Master's theorem for decreasing functions just focuses on the value of a. It is the value of a which decides what will be the solution of the recurrence without solving it. So a could be also less than 1. Less than 1 means what? It's not negative, but it is between 0 and 1. It is less than 1, but it's greater than 0. So in such cases, the solution is just we have to take the order of function directly f of n. Okay, so if we are having something like here, it is given as 5 divided by 8. Okay, this will be less than 1, and then the function is t of n minus 1 plus n. So its solution will be when it is in decimal points, it's less than 1 but greater than 0. In such type of recurrences, the solution will be just take the order of the function term, that is this term. We don't have to multiply it by n, we don't have to multiply it by a to the power n. So it will be direct order of n in those cases. And this is the general, if you are appearing for some competitive level of exam, you have to just keep this master's theorem for decreasing functions in your mind to solve it in a very less period of time. But this is the case for decreasing functions. So for decreasing functions, all the three methods are covered, whether these are the recursive tree method, substitution method, or it could be the general form for the decreasing functions. Now we will shift to the dividing functions and study about some of its cases. And dividing functions, as we said, that any recursive function needs to use a program step which will keep on decreasing its value by some parameter, so that a time will come when it keeps on decreasing, it will reach to a value where it will terminate. Because if a software does not terminate or it does not output a value for us, it will go in an indefinite loop. That's not of any importance to us. But now, this decreasing of parameter could be either in this form, it could be also in this form. And for such type of functions, we have solved it and we called it a decreasing. And for such type of functions, we call it dividing functions. Because if initially n was equal to 100, so in the second case, when the recursive function will be called again, it will be half of that. So means the recursive function is computing as well as it is moving towards its termination. So now we will see the cases when our recurrence relation will be of this nature. Then what is the way to solve such function? So as usual, we will start by a program and we will use the condition that if greater than 1, because we can't use now 0 here as it is a dividing function. So we will tell it if this case is true, then keep on printing the value of n. And to make it as a recursive at each step, keep on calling itself by using a dividing parameter by 2. And this way it becomes both a recursive as well as a dividing function. So we will now see how to solve such type of program segments using either of the methods. Three methods for dividing function also, like for decreasing. So as usual, we will start it as we did it in the previous classes. This will be the time complexity of whole of the program. And this will be the time complexity at each time it makes a recursive call to its sub-program, or you can say the sub-function inside this program. And for it, it will be 1 because there is no for loop. At a particular time, it will be executed only once. Now, to write down the recurrence relation for such a program, this program, recurrence relation is of the form that is T of n will be equal to two cases again. If n is equal to 1, means we take any constant value. And we saw in the decreasing functions that whatever the value we take here, it does not matter. If we take unit as C, it again produces the same results. This means when n is equal to 1 here, n is equal to 1, we are making the comparison only once. So it will take constant amount of, it does not do anything at a time, but comparison it still does. Okay. Now, if this n becomes greater than 1, so this statement then executes because the condition gets true. So in this statement inside the F, we know there are two main statements. One is the recursive call to the function, another is the print statement, that's 1. Okay, so to solve such, this becomes a recursive call of dividing nature. And to solve recurrence means to remove this t from its equation. And if we see the two conditions, in the first one, no t, So what we have to do is to solve this part of the recurrence. And that is what we mean by saying that we are solving the recurrence relation. So we will write it down here again, the part which we have to solve, that is T of n is equal to T of n by 2 plus 1. Now we will start our logic. The first one is using recursive tree method. Recursive tree method says that this T of n, at each time it will take this much of time, or it will, you can say, it will print this value of 1 and will call itself, it's not 1, call itself by decreasing the parameter half of the times, because this is what we use it as a recursive function, by decreasing its value by dividing 2 at each iteration of the program. So now again here, this recursive call itself will print this statement again, that's n, whatever the value of n is, and it will call itself one more time, that's n by 2 power. Yes, 1 power, or it will be decreased by 1 by 2 factor at each iteration. So again, if we see this recursive call, T of n by 2 square, it will print the value of 1, which will be the value of n at that very time, which will take one step, and it will be calling itself by n by 2 power 3. Sure. And this process, suppose this I call as iteration number 1, this I call as iteration number 2, this I call as iteration number 3. So if I have to find for iteration number k, it means for iteration number k, this man for recursive call will go up to n divided by 2 to the power k. Because here it is third iteration, so 2 is raised to the power 3. Here it is second equation or second iteration, 2 is raised to the power 2. So again, similarly, to find a sequence, if it is the kth iteration, as we are saying, so it will be t n divided by 2 to the power of k. So initial value of t of n is equal to 1 when n is equal to 1. This is known to me from the recurrence of this equation here. When n is equal to 1, t of n is equal to 1, which means t of 1 is equal to 1. Isn't that? So in order to find this value of t of 1, what I had to substitute equal to 1, n. Whatever is present inside the brackets of the t, I have to substitute it equal to 1. Then I will get this t of n, t of 1 equal to 1. Yes, from the recurrence itself. Now for the kth iteration, that is this one, if I will get it equal to t of 1, I had to make it equal to t of 1. So what does it mean? I had to substitute n divided by 2 to the power k equal to 1. That's what it means. So it could be also written as n is equal to 2 to the power k by multiplying. So taking log on both sides, this will be equal to log of n is equal to, this will be k, because it is log m to the power n. It will come, k will come here, it will become log 2 to the power 2, and that's equal to 1. So in short, k will be equal to log of n. Isn't that? K will be equal to log of n. Now if I see how many program steps it will be having, here it is 1, 1, 1, 1, 1, 1, and this number of program steps will be how many in the whole program? k. Because 1 plus 1 plus 1 plus 1, it will be n or k, whatever you denoted. So the total t of n of this program will be k into 1. 1 is always it takes one program step to print the value, and how many times that will depend upon the k, the number of iterations. So I can write it as t of n for this program is equal to, since it is equal to k, and my k for kth instance is equal to log of n, so the total time for this recurrence will be in terms of logarithmic. And the final solution is without the t terms, and we can proudly say that yes, we have been able to solve such recurrence. Now see, if t of n we say is equal to t of n by 2 plus 1. Now taking substitution, which is the second method, into consideration, the substitution method says that we have to substitute something in its place. Since our goal is to remove this t term, so always we will try to find whether we could be able to substitute some value in place of this t that will be without t. Yes. So we will write down this whole equation here. T of n is equal to t of n divided by 2 plus 1. So I will try to find t of n by 2. And this I will denote by equation number 1. So I will try to find t of n by 2, so that I will substitute that t of n by 2 here in this equation number 1. So for t of n by 2 means what? As we saw in the decreasing case, that in place of n we have to substitute n by 2. That's how what it means. So this will be t. So this one will be 1 by 2 itself, 1 by 2 into, here in place of this n we have to substitute n by 2 again. And this plus is already from the equation, because this is the whole equation, and here this is for this part, plus 1 is already there. So t of n by 2 will be equal to t of n divided by 2 square plus 1. Name this as equation number A. So we found the value of t of n by 2. From equation A, let's take t of n by 2 equal to t of n by 2 square plus 1 and substitute it in equation 1. Equation 1. So equation 1 is t of n, this part, equal to t of n by 2. This is equal to whole of this, whole of this. So in place of t of n by 2, we can write t of n by 2 square plus this 1, because this is the whole which we have to write here in place of it. Then this plus is again from this formula. I hope you are able to follow me. So t of n could be again written as t of n divided by 2 square plus 2. Let's keep it as equation number 2. Simple. Now, to simplify this equation 2, we should be able to know the value of this term, so that, like we did in equation first, we can be able to substitute the value here in its place. So t of n by 2 square, I have to find its value. Yes. So again, I will go to the equation first. In place of n, now I have to substitute n by 2 square. So already 1 by 2 is its multiplier or a factor by which it is multiplied. And in place of n, I have to simply substitute n by 2 square. Sure. And then comes the 1 of this equation itself. No such rocket science. T of n by 2 square is again equal to t of n divided by 2 cube plus 1. Mark it as equation B. So like we did in the previous step, we will take the value of n by 2 square from equation B and substitute it in equation number 2 here. So in place of t of n by 2 square, this whole value we will substitute it here. That means t of n will be equal to t of n by 2 square, the whole, this thing, t of n by 2 cube plus this 1 from equation B plus this 2 from equation 2. No change in its value. So that means t of n will be equal to t of n divided by 2 cube plus 3, denoted equation number 3. So if we see the equation 1, equation 2 and equation 3, there definitely is a pattern present in the equations. What is that pattern? When it is equation number 1, okay, that equation number 1 is raised to the power of this 2. 2 to the power 1, that will again be equal to 1, 2. When it is equation number 2, 2 is raised to the power of 2 and that 2 is also added here. When it is equation number 3, 2 is raised to the power of 3 and that 3 is also added here. So by this, we can be able to show that if we keep on going in the same logic and go for teeth equation or teeth instance, whatever you call it, so we will be able to find t of n. It will be equal to n divided by 2 power equation number. Let's keep it as kth equation. 2 power k plus, again in place of 3, it will be equal to k. That will be for kth. Yes. Now, what I am interested in this part, to remove the t. To remove the t means that n by 2 to the power k should be equal to 1. Then it will become t of 1, that's equal to 1. So again here, after getting the log from both sides, it will be log to the power log to the base n. Log n short. So moving it again for t of n, that is this term will be equal to t of n by 2 power k is equal to 1 plus in place of k it's equal to log of n. So t of 1 is equal to 1 plus log of n. That's all again equal to the order of log n, which we got from this method also. That's from the recursive tree method. So you are 6 people here. How many are able to understand or how many you are not able to? You? Okay. Okay. So without taking a program segment, we will now take a second case or a second example directly as a recurrence relation. The recurrence relation will be again equal to, if it is 0, sorry, if it is equal to 1, then it's 1. If it is greater than 1, then recurrence is calling itself in place of 1, it's n. Yes, the same example is there in decreasing functions also, but here we are taking it in the dividing case. So what we have to solve is this one. So to solve n divided by 2 plus n. To find its solution using the pattern number 1 is the using recursive technique. For recursive again, we will be writing it t of n. T of n will be giving the value n and will be also calling t of n by 2. T of n in the same way. In place of n, again, now it will be substituting n by 2. And it will be calling itself n by 2 to the power 2. The same logic. T of n by 2 square, it will be calling itself 2 square and will make a recursive call by decreasing its parameter 2 of 3. And this will go on until we reach to the kth part. Kth part or kth iteration means T of n divided by 2 to the power k, and here it will be printing then n 2 to the power k minus 1. Simple. Now we have been seeing so many examples of this type. Now to write down this as the sum of whole the program steps, it will be n plus n by 2, n by 2 square plus n by 2 cube plus going on n by 2 to the power k minus 1. Okay, so T of n will be again equal to, we will take 1 as n as common, and inside we will get 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 power 3 plus going on 1 by 2 power k minus 1. So this will be again equal to T of n equal to n. I can write it down as I can write it like this also. So if we now see this value, this is equal to 1, but how? Just given an example how it is equal to 1. So this is what I'm talking about, this part. Leave this one. Okay, I'm talking about this part. So it is equal to 1 by 2 plus 1 by 4 plus 1 by 8. This is how it is equal to. So if we take a circle, okay, the circle is whole equal to 1, whole circle. Now if we divide it into two parts, this much will be equal to how much? 1 by 2. Okay, half of the total. Now this half is again divided into two halves. So this much will be equal to how much? 1 by 2 square means 1 by 4. So 1 by 2 square is again divided into two parts. So it will be 1 by 2 cube. Yes. This is again divided into two parts. So this part will be equal to 1 by 2 power 4. So this will go on. But if we now sum up all those little parts, 1 by 2, 1 by 2 square, 1 by 2 to the power cube, we go on to the power something k. So it should be equal to 1 because these are the little parts of the whole circle. The summation will end up to the 1. So this is the sequence here also, this sequence. So mathematically, this sequence should be equal to n. Internally, it will be 1, this one, plus this whole will be equal to 1. So T of n will be again equal to 2n, which will be in terms of asymptotic notation equal to order of n. And that will be the time complexity of this program segment. Any doubt in it? Now, the second case is the substitution. So if I take any one of the students here in my place and tell him to solve, I hope you will be able to solve it. This was the actual recurrence. Now, Solving means what? No, no, I don't mean it. I don't mean it. The point was that you should be bold enough to know the answer or to how to solve it. It's up to you whether you make this. I will share all of those this even those whiteboard whatever I'm writing. I will share it in the group. So T of n again using the substitution method. I need to solve it. The solution I can be able to find is that I have to find the value of T of n by 2. So to find the value of T of n by 2 in the original equation, which is this one, I had to substitute n by 2 every place where there is n. So taking this 1 by 2, which is factor to it as outside, so as to make you understand how we substitute this value. Otherwise, you can directly do it. So now there is n in place of n, we will write it n by 2 plus. Then again there is n in place of n, again n by 2. This is for T of n by 2. So the original recurrence was T of n is equal to T of n by 2 plus n. Equation number 1, T of n by 2 we got that's equal to this much. Mark it as equation number A. So as per our historical solutions, we will take it from A and substitute it here. So in place of this T of n by 2. So this plus 1 is untouched. We did not did anything with it. It will be kept as such. Now only T of n by 2 we changed, and the change is equal to this. T of this will be n by 2 square plus n by 2 plus this n as such from this formula. So this will be equation number 2. To search for n by 2 square, which means from this equation, this term will remain unchanged because we had to only substitute something to its place. So n by 2 will be as such plus this n will be as such. So something is to be added to this term to make it equal to T of n. And that something is whatever we get T of n by 2 square equal to. T of n divided by 2 square, again we will revert back to the original equation. T 1 by 2 will be taken as a multiplier, and in place of n, it will be n divided by 2 square. Plus the original equation have got n, which will be n by 2 square after substituting in place of n. Denoting this equation by equation number B, again following the logic of substituting T of n by 2 square from equation B to equation number 2. These terms will remain unchanged. So in place of T of n by 2 square, this whole could be added here. So it will be equal to T of n divided by 2 cube plus n divided by 2 square plus this is already there, n by 2 plus n, and we will substitute it as equation number 3. So finding the same sequence for kth equation. For kth equation, if we write this recurrence again, this will be equal to T divided by n 2 to the power k, because when it was second, 2 to the power 2. When it was third, 2 to the power 3. When it will be kth, 2 to the power k plus n divided by 2 to the power k minus 1. plus n divided by 2 to the power k minus 2 plus dash 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 dash, and it will go up to when there will be no k involved, means n. So again, to make it equal to t of 1, what we assume is that n by 2 power k should be equal to 1, which will again give us k equal to log of n. So t of n, this equation will become t of n equal to t. In place of this, it will be 1 plus. This will be n divided by, again we will take n common here, sure. So it will be here, then we will write it in the reverse order. N will be initially here, when we took it common, it will be 1 here in this place. Similarly, it will go up, go up here, it will be n, it will be 1 divided by 2 to the power of k minus 2 plus 1 divided by 2 to the power of k minus 1 in the reverse order. Writing from here to here, n is common, sure. So t of n will be equal to t of 1, we know that's equal to 1 plus n, this n plus this is equal to again 1. And this is again equal to the same equation, that's 1 by 2 plus 1 by 2 square plus 1 by 2 cube. Because if we write the terms after 1, it will be 1 by 2 plus 1 by 2 square. And this way it keeps on adding. Okay. So this is 1 plus this whole will be again equal to 1 as per the previous formula in which we discussed about the circle. T of n is equal to 1 plus 2n. So again, only the instantaneous characteristics is nth term. So in terms of asymptotic notation, it will be equal to order of n. So I will stop here. Huh?